Uh, right, so I won't take too long. So I'm Stephan, I'm at Stellenbosch. I graduated in June from my PhD at Westhuizen. You can see there's a picture of the very flat Netherlands to the left. And this PhD was done in digital soil mapping. So I'm starting to sound like the soil guy in SASA. But yeah, so all my projects are basically in this field with the different challenges are basically driving my different projects that I try to work on. And Inga wasn't lying. She was one of my examiners. You can see there she is in the very red UV colors at the graduation ceremony. So I will briefly go through just what is DSM for those of you who don't know, and then I'll basically run through some challenges as to what are the projects that I'm working on and that I will hopefully get more funding for. So DSM is quite a big field, and it's becoming very prominent in the last 10 years because soil is a very important resource in the world. And so basically how it works is that you have a point map. So you can see to the left, the orange with the black dots. And at those points, you basically have a realization of some spatial process. In this case, this will be your soil property. So these are locations that were either directly sampled or it was just some sort of convenient sampling obtained from some soil database. And then you would overlay this in a GIS with satellite imagery. This is mainly driven by what drives the distribution of soil. So we talk about the Clark model or the Scorpan model. These are typical things that you should include into your list of covariates that drives the distribution of soil, like climate, organisms, and so on. And then you tabulate this, everything, you build a model, and you try to estimate your f of x. You do your final prediction map, and if necessary, you can also do some geostatistics on your residuals. So just briefly, always, why do I map soil? Why do I work? I've come to be very fond of this research and this type of research. But something that's very interesting for me that I will highlight now is that it takes a lot of time for just a few centimeters of soil to be produced. So this last bullet point. So it's very important for us to know what the soil looks like and how and what remains and how to measure it and so on. And this is also why it's also very nice for research applications in terms of getting funding, because a lot of governments all over the world are starting to develop frameworks, legal frameworks to try and protect soil. So we see this in the entire first world. It's starting to happen in South Africa, which is also very good news. So from a statistician's point of view, where are we involved? So we are obviously not involved with, well, in most cases, not really that involved with obtaining data, but basically we are involved in steps 1, 2, 3, and 4 that I visualized here. So my projects are mostly about step 1, so trying to get that framework ready to get a model that can predict soil over the entire region. And I also started to look into, so in digital soil mapping, we're also very, very interested in the mechanisms that drive soil. And so for that, interpreting or using interpretive machine learning is also becoming greatly used and very exciting. So just a little bit of background. So traditionally, geostatistics has mainly been used for DSM, but in the last 5 to 10 years, machine learning is really starting to dominate this field. And for various obvious reasons, like you have models that can handle more complex data, you have definitely increased map accuracy, you don't need a lot of assumptions, but you will see that I've added there in red, but there's also a lot of abuse. And I've started to notice this as I started to review papers for other journals in the last year. But also in terms of machine learning, you don't really quantify your uncertainties, you don't directly account for spatial information, There's this trade-off between accuracy, model, and interpretability. And there's also data-related, like data challenges that I also focus on in my projects. So for example, I will go through some of these that I think was quite interesting. And then if people want to ask questions about that afterwards. So the one recent study that I've got published is censored soil data, which is a very big problem in the community. So essentially it's a survival problem, but not time-wise, but more vertical depth-wise. So you can see, for example, in the schematic illustration to the right, you have the surface, let's call that D0. And then you have the true soil thickness, let's say this dashed line over here. And at application A, for whatever reason, you didn't observe the true soil thickness. And then at application B, you did observe the soil thickness. And then you would like to map this actual dashed line, but obviously it's very problematic because you have a lot of locations where you don't actually know what the true soil thickness is. And what makes this even more difficult is that you have a lot of different definitions of what soil thickness is. This is a very complex problem in soil science that I'm not an expert in. So different countries will have different definitions of soil thickness. So you have this problem of really trying to merge all these kinds of things into one database and then try to work in that framework. So what we've done in this paper is it was actually a straightforward approach. Well, straightforward for people maybe in survival analysis, but I was new in survival analysis. But basically what we try to do is to estimate weights, and these weights were inversely proportional to survival probabilities. So for example, we estimated survival probabilities at locations where you had non-censored observations, and then obviously you would like them to contribute more to the model compared to locations where you didn't have the actual observation. And this worked quite well. There's a link here for the paper if you want to go look at it. But there's still remaining problems in this work. So it's not a typical survival analysis problem where you're trying to understand the occurrence of death or when the time will be or when the death will be. It's more at the specific death, giving all the data and the covariance. You want to predict the actual event, not the probability of the event, if that makes sense. So that makes model calibration and the way we evaluate maps very difficult. For example, if in your validation data, you obviously have data that's also censored. So how do you technically take that into account? So one simple method that we implemented to evaluate maps for soil thickness is that we derived maps only up to a certain thickness. So let's say only the first meter. And you treat all observations, if they were predicted in that first meter, as true, if the actual thickness was considered in that first meter, or if the censored was also within that first meter. It was a nice solution because it was a very pragmatic solution for people who are interested only in the first meter and they don't really care if the soil thickness is deeper than that. Because most in agriculture plants, they shoot roots and they only need a meter of soil to effectively grow, and they don't care if the soil thickness is deeper than that, so to say. So this was a nice data challenge. So there's definitely more research to do here. This is just some extract from that paper where we reproduced maps and the case studies that we worked with. I'm just going to move on to another data challenge. So this is something that I'm also now got new funding for. Most soil properties are bounded in some way. So for example, you have properties like clay, salt, and sand, and they are bounded by 0, 1 or 0, 100%. So these are composites. And so there are a lot of ways of doing transformations where you can use transformations to map these variables from the simplex to your actual feature space, or not feature space, but space where you want to work with. And so a lot of times those transformations actually induce a little bit of bias into your predictions. So we're trying to develop machine learning. And this is where I got a very clever postdoc for that will help us with this. So we're doing machine learning that will directly map these soil properties in the simplex, and you don't need to require transformations. You can hear that I'm not a big expert on this field yet, but I'm getting there. Other challenges are uncertain soil data. So this was my first chapter of my PhD. Basically, when soils are measured, there's errors involved with the entire process, and how do we account for those errors in the modeling process? Another problem was, what if you wanted to map not just a single soil property, but you wanted to map many soil properties, and you also want derivatives of those soil properties. So we looked at a paper that used multivariate machine learning to do that. So here you have, for example, carbon and nitrogen that was mapped for Germany, the Netherlands, and Belgium. And then from these soil properties, you want to derive derivatives such as the CN ratio. So these are measures that soil scientists use to measure how healthy the soil is. And this was also quite a nice study. And there's also a lot of work that will be done in this area. And then last of all, some work that I'm currently working with, and I'm trying to get a paper published on this, is using visualization methods to help us better understand how the machine learning goes about making or producing its predictions. So this is, for those of you working in IML, there are currently some stuff that you can do, for example, using partial dependence plots, Shapley values, and we are basically trying to do this with biplots. So the case study was South Africa. So South Africa, we mapped carbon, and now we want to understand how the environmental covariates relate to the spatial distribution of carbon in this country. Sorry, I'm just going to skip this. This is other methods. So we're basically using biplots to where we constructed biplots on a selection of covariates. So these axes represent your covariates, and then the color arrangements are your predictions, and you're trying to understand when do you predict high carbon, when do you predict low carbon. And so currently this is a biplot on the predictions, but we're also trying to do this multivariate approach with, let's suppose that you look at very local changes and you try to biplot the local changes themselves, and how do those then map in the biplot to better understand the relationship between the covariates and predictions. Yeah, so those are some examples. Obviously, some other challenges that I'm also working on in collaboration with other people is machine learning or spatial machine learning. If you can develop a good spatial fast method, you will get a lot of citations. So hopefully we will contribute to something like this in the future. But yeah, I think that's mainly it, what I wanted to share today.